the presentation. Well, Professor, well, thank you all of you for being here. Professor Alexandre Zagoskin, he's reader in quantum physics in the physics department at Loughborough University in the UK. He's one of the founders of D-Wave Systems, one of the first quantum computing company, if not the first. His studies and long-term positions include the A.M. Gorky State University in Kharkov, Ukraine, the V.I. Birkin Institute for Low Temperature Physics and Engineering, also in Kharkov, the Chalmers University of Technology in Gothenburg, Sweden, University of British Columbia, Vancouver, Canada, and BP Research and Chief Scientist at D-Wave Systems. His visiting positions include the University of Sherbrooke, Riken at Japan, and University of Notre Dame, South Bend, USA. His main goal is to develop and make quantum engineering into a self-sufficient discipline. Well, Professor, it's up to you.
Thank you very much. I'm grateful for this kind invitation, and I'm going to tell about the development of quantum technologies and quantum engineering. I was fortunate enough to jump in right when the whole thing started developing. So if you give me a second, I will share with you my screen and we'll start. Right? So please don't hesitate interrupting me, asking questions. This is the standard way of running seminars. Now at Loughborough, we also have this Landau seminar, again, named after Lev Landau, and exactly because this is running in this traditional way. You can ask questions any moment, and if you think you can answer better than the speaker, you do it. And this makes long but very interesting meetings. All right. Can you hear me fine?
Yes, there's a little bit of echo. I don't know if you don't have, let's say, but there is any problem. You are muted right now, Professor. Right now, we can't hear you because you are muted.
Can you hear me now?
Yeah, sure. Right.
Very good. So, first of all, well, you know, I couldn't help myself, and a little twist this title of the famous short story by Borges, which is kind of a very nice description of quantum theory, in a sense. And now we are all working on making this quantum effects visible and working on large scale. So, yes, I was fortunate enough to study at Kharkov State University, one of the oldest universities in the Russian Empire and one of the best. I was fortunate in my teachers. I studied physics with Kanner, of Asbel-Kanner resonance. I was studying with Igor Janssen, and I just missed on studying under Ilya Lifshitz. This was a great time. This was great opportunity. And Kharkov at the time was probably second most important scientific center in the Soviet Union, maybe third after, at least in physics, after Moscow and maybe Novosibirsk. So it was a great place to be. Then I went to work at Institute for Low Temperature Physics and Engineering, FTINT, again, working under supervision of Igor Kulik, working with Emelinchuk and Schachter, well, with such mathematicians and physicists working there, like Pastor, like Kredeskel, who tragically died on the 7th of October, when long ago in retirement. This was a unique opportunity, and then moved on to a number of other very, very good places, in particular University of British Columbia, where my postdoctoral supervisor was Ian Affleck. So I published several books, and the one which has a direct relation to today's topic is quantum engineering. Now, well, this one was published 14 years ago, so a new edition is due next year, because lots of things have happened in this very quickly developing field. So why again quantum engineering? This is all a question of timing. We are living in the time of a second quantum revolution, which started roughly in 1999. What is it about? To begin with, the first quantum revolution, this is something which happened about 70, 80 years ago. This is when quantum mechanics was first used kind of on industrial scale. With the development of nuclear weapons, as usual, the military is the best friend of physics, however sad it is. With the development of nuclear power, which is our currently best chance for producing enough energy for the functioning of an industrial society without overheating the planet. The invention of semiconductor-based devices, which would be impossible without quantum theory of solid state, lasers, superconductors. Practically all of our current technology, to some degree, depends on the results of this first quantum revolution. The fact that I can talk to you right now is the best evidence that we understand what we're talking about, and we can use these results. But why it was, say, first quantum revolution? Because all these physical effects, all the specifically quantum effects on which this phenomena depend, they're all on small scale. Even when we talk about quantum microscopic wave function describing, for example, superfluid helium or superconductor, this must be taken with a grain of salt, because we don't scale quantum correlations here, not something which involves many variables. After all, the superconducting order parameter can be described by just a single complex number at every point. And mathematically, it is described by two-point correlators. What was the qualitative difference brought about by the second quantum revolution? This is when we managed to produce quantum superpositions and quantum entanglement involving large number of microscopic quantum states, and when they exist over macroscopic distances. This is what enabled quantum computers, say even the primitive digital quantum computer that we managed to produce, but also quite operational analog quantum devices, quantum simulators, and even quantum communications, even though here we must be cautious because quantum communications do not require superpositions and entanglement of large number of single electrons or single particle states. But this is a very significant progress which was reached, well, an experiment since say 1999. But you know that this year Nobel Prize in Physics was awarded for the discovery of macroscopic quantum tunneling in a superconducting system. This is an important thing. This was not sufficient but necessary for the realization of other facts which are vitally important for the operations of a quantum computer. Well, you can trace it back to a paper and talk by Feynman in 1981, and independently to a short bit, about half a page, in the preface to Manin's book on calculable and incalculable, which was published only in Russian and so was not noticed abroad. But the point was the same, that a large quantum system has exponentially large state space and therefore cannot be efficiently described by classical means. So you need a quantum computer in order to properly model a quantum system in all detail. Why we can efficiently build the quantum theory, say, of semiconductors or superconductors, this is exactly because we are not looking for all possible correlations, but only for small-scale ones. So, well, be it as it may, quantum revolution started in the 90s. Funny thing is that it was spurred on by computer science. You almost know what a stir was created by Peter Shor with his discovery that standard public key encryption can be broken by a quantum computer. It doesn't matter that you don't have yet any physical possibility of building such a quantum computer, or that when you have efficient quantum key distribution, you don't need to worry because you don't need a public key system to safely protect your very sensitive data. But as usual, you had some state actors who were very concerned that breaking of this code would be really dangerous. As one of these guys said somewhere in the lobby during the first quantum computing conference in Sydney, year 2000. It doesn't matter if there is even a remote chance that in 20 years somebody will be able to break this code. We should change our routines and protocols right now. Well, as we all know, the real threat to encrypted communications is not coming from technology, it comes from humans. But that's a different story. Anyway, this is what caused a huge influx of funding in this field, and this is what allowed people to actually try and build quantum bits. So why superconductors? Because they are convenient, they have kind of built-in mechanism which protects you from all kinds of noise and decoherence, and also very important that we do have very good technology developed over decades. Because the Josephson effect, I don't know whether I need to explain what it is, but I assume that you know, and if you don't, let me ask me and I will tell. But the idea is that your supercurrent can flow through a weak link, be it tunneling barrier or a constriction or anything else, and it can flow without dissipation. As a result, this Josephson junction can play the role of a tunable inductance. And what is the key thing is that the voltage across such a junction is related to the speed with which superconducting phase changes across it. For some reasons, it is almost always easier to measure time than anything else. So if you can reduce voltage to measurement of some frequency, it allows you to produce a very good voltage standard. And this is where much money was, and this is where technology was developed. So by the time it became clear that it is interesting and possible to make quantum bits out of superconductors, technology needed to produce complex enough superconducting systems was already there. And several types of superconducting qubits were developed very quickly. So the charge qubit, where you have a small island where extra Cooper pair produces significant voltage change, and so you can tell, and you can produce a superposition of states with and without this extra Cooper pair. The flux qubits, several types, essentially where you can have superconducting current which flows simultaneously clockwise and counterclockwise along the superconducting loop. The so-called phase qubit, the simplest one, which is just a current biased Josephson junction. All of them were realized, and the charge qubit by Nakamura, Pashkin, and Tsai, different flux qubits by Lukin's group and by Moy's group, phase qubit by the group of Martinez. This was all done pretty fast between 1999 and 2002. So why we are still so much interested in these things? If all this was of very narrow military, or if you wish, intelligence kind of interest, this activity would not have proceeded very far. It would be very narrow niche kind of research. But you know that now we have a lot of activities going on. First, there is the real scientific reason why we should be interested. Because if we manage to make large quantum structures existing in superpositions of states, demonstrating entanglement, that is, making bigger and bigger Schrödinger's cats, this allows us to test the limits of applicability of quantum mechanics. And frankly, we are not in a very good position right now. Look, 100 years ago, when quantum mechanics were just being built, every time theorists ran into some problem or came up with some beautiful but wrong ideas, there was always an experiment which immediately brought them back to the Earth. And not just that, but also provided them with very clear direction where to go. Like Gerlach-Stern experiment, for example. Now, no, the most frustrating thing, at least for me, from all this more than 2 decades of success is that we still did not find any single indication that quantum mechanics is going to break down. No matter how big the device is, somehow, as soon as we manage to control the decoherence, it demonstrates quantum property. So from the scientific point of view, we should build them bigger and bigger until they fail. And then we'll try to figure out what was wrong. But in order to figure it out, we need actually to build quantum engineering, and I will return to this later. But why are we getting funding for this? Why do we have so many quantum computing companies on the market? This is an interesting question. And of course, as Landau used to say, money isn't the exponent. So you must count money accurately. So the estimate for quantum computing market, close to $2 billion next year. It looks like a little of, beautiful understatement. Let's see how people looked at it, say, 10 years ago. 10 years ago, 11 years ago, the British state organizations estimated 5 to 15 years to practical applications of different quantum devices. So, and prediction that in 2035, quantum computers will be already way ahead of classical ones. And estimation for global markets at that time was, of course, wildly jumping between 1 million to 10 billion pounds. The expectations for applications are both in algorithm and communications, in simulation, in quantum chemistry, and in quantum machine learning. Well, of course, again, 10 years ago, the 1.5 billion euros of global expense, well, I'm not sure that it was accurate, but now, then the predictions were about 11 billion. And this is, again, a beautiful understatement. Because last year, the estimate of global quantum spent on by governments and in the open programs, not some classified ones, already exceeded $38 billion. With every country which had something to spend, did spend quite a lot. Of course, you cannot tell exactly how much Americans spent, how much Russians or Chinese spent on this, but even the available data show that people are really, really interested, because quantum tech indeed promises lots of interesting things. And of course, all this talk about quantum supremacy, which nobody really knows what it is and what it's supposed to be, but everybody tries to get this further. Again, because this will give you bragging rights and more investment. Well, you have also, of course, mistakes, missteps. You can have this attempt to make a Majorana qubit, which failed because it was based on, I would say, not quite reliable data, but effort is here. Lots of effort, and lots of things depend very much on how they are presented. Too much of this stuff is really dependent on hype, on public relations, but there is a solid core underneath all of this. Well, we don't know whether universal quantum computing is feasible at all or in near future, but this is not the only quantum technology. There are lots of other quantum technologies which provide more opportunities, more interesting things from the scientific point of view, and of course, more competition as well. Right? So, simulation. Quantum simulation is already shown to be very powerful. Quantum sensing, imaging, quantum optimization, which already has commercial applications. Well, the latest I did here, Northern Wales Constabulary, that's police force, is using one of these quantum annealers online in order to quickly distribute the available forces in the most efficient way. And we have now developing quantum neural networks or machine learning or hybridization of quantum computation and artificial intelligence. One significant thing which people until quite recently did not properly take into account is that quantum machines, even if they are not providing, say, much better results than classical ones, may be better because they are cheaper, because they take much less electricity. And the question about greediness of artificial intelligence is already quite significant. In this sense, quantum computers may do to classical ones the same thing that early firearms did to archery. You must know that the reason why firearms replaced archery in European armies was not because they were shooting better. Actually, they were shooting worse, slower, much less accurate, but they were cheaper. Not even by themselves, even though a good bow would be quite costly, but if you take into account the necessary training. To train an archer would take years. But almost anybody, any country bumpkin, can be taught to use a firearm. And if this firearm blows up, it is cheap enough to replace both the firearm and the shooter. So this is also a consideration. As I said, one serious thing that quantum computers, whatever kind, can demonstrate is they don't need this much energy for comparable kind of computation. Now how I managed to land in this interesting field. Well, I've put this history in all places, a paper in a Journal of Physical Society of Japan, but roughly this happened this way. At that time, I was interested in high temperature superconductivity, in particular in D-wave junctions. I found theoretically that such a D-wave junction would have a bistable characteristics, so that its potential energy will have two minima. So this would correspond to, in principle, a possibility of making a quantum bit. At that time, nobody was talking much about quantum bits. And together with Masaki Oshikawa, very distinguished professor in Tokyo, at that time, he and I were both postdocs in Ian Affleck's department group at Vancouver, University of British Columbia. So we decided to think what happens if we manage to make kind of a ring out of high temperature superconductors. Then there would be tangential currents, and the whole thing, in principle, could play the role of a qubit. Only, unfortunately, it was not likely in case of realistic size of this whole thing. So we didn't write anything about the properties like for a qubit that it could be in superposition and so on. No, because we didn't, in this particular case, we didn't estimate that it can happen. But then I also was spending some time at University of Sherbrooke, and there I thought up a way of calculating thing for this kind of device. And here, if you had a conventional superconductor in between, you could have a chance of making it into a qubit. Well, this is, of course, an extremely naive picture. Nobody in their right mind would ever try to do this in experiment, but as a Gedanken experiment, it was fine, I guess. And then I and Alexandre Blaise, who was then a student there, we wrote a paper on this. And when I returned to University of British Columbia, I was walking the corridors and telling everybody who would like to listen that if I have $1 million, I know how to build a quantum computer. And somebody was actually listening. So George Rose, who was then a PhD student, and we before that worked on some kind of competition, proposing a method of using two-dimensional calculus for classifying fingerprints for places and all problems. We didn't get the prize, came to know each other. So he came to me and said, well, okay, if I will get $1 million, will you actually try? I said, all right, let's do it. I was about 2 orders of magnitude wrong, of course, concerning how much it would cost. So it turned out that Georgia knew Hake Ferris. Hake is one of prominent angel investors in Canada, and he was given a course on entrepreneurship at the department at the time. So as a result, we met and we established this company, D-Wave Systems. Why we call it D-Wave Systems? Because initially we really wanted to make these qubits out of high temperature superconductors, so that you see these systems would have naturally doubly degenerate ground state, so that you wouldn't need to bother with external fields in order to bring it to the proper convenient state. So this is why we called it this way. And this is our happy company with Bob Vince on the left, who was our first chief financial officer, and very interesting guy, really passionate about accountancy, and a biker. So we had an interesting group, really, because Jordi, he was an Olympic class wrestler. Well, I just had the black belt, so it was not much, but still. And we started our operations, starting with this check for $4,000 odd, which was necessary for me to go to a conference in Finland to talk to my contacts at Chalmers University of Technology, where I was before that, because we needed somebody who could do experiments. And there I also met Evgeny Ilichov from Jena Institute for High Physical Technologies. Now it is Institute for Photonic Technologies, and we still collaborate. And things started rolling. Well, it was interesting. While we've been driving around Vancouver, talking to different investors, it was not easy because it was just 1999. It was the dot-com boom. So people who knew that they can make money in 6 months investing in some software company, it was hard to persuade them that they can make money in 20 years' time if they invest in quantum computing. But some people actually did, and I think they did not. They were not sorry as a result. But every day driving around the place, every morning, a car was picking me up, and we in suits in dark shades with briefcases and going somewhere. So eventually our neighbors started asking whether I'm actually a physicist, because it didn't look very much like what they thought a physicist would look like and behave. Anyway, as a result, we managed to bring together a good group of people from the Ukraine, from Slovakia, from Sweden, Germany, the Netherlands, UK, from National Physical Lab, and of course from the States. This was our first logo, D-Wave, because of symmetry of high temperature superconductors. Then there was another logo, and then the one that you can see if you look at the company's website. And we did pretty well. It was not just, attempts to build a quantum computer. It also had quite a lot of interesting physical results. So, for example, one of the first demonstrations that you can have in two flux qubits entangled states, or investigation of high temperature superconductor based qubits. like this one. In the process, we also demonstrated that actually high temperature superconductors do have D-wave symmetry by investigating the Josephson junction between two such superconductors, showing that indeed we have this bistable state, degenerate state, in full agreement with theory. That was great. Unfortunately, Zdravko Ivanov, who was the lead for this high TC research at Chalmers University in Gothenburg, he left us early, tragically, and we had to concentrate on low temperature superconductors only. And a little later, macroscopic quantum tunneling in D-wave superconductors was actually demonstrated a few years after we stopped. So, but at any rate, it is a vindication. We would come there if we didn't have to concentrate elsewhere. So we did. This is something that was done by our group at Institute for Physical Technologies in Jena. Leibniz Institute is now called. So with flux qubits and demonstration of this entanglement that I mentioned, you see here these two loops with each of them is a qubit, which can carry current simultaneously in two directions. And this is single qubit, and in this qubit we managed to measure Rabi oscillations. And well, actually what you see here is demonstration that you can observe these quantum oscillations because you have the systematic change in the noise level, noise spectrum of the system as you change the frequency of a pumping field. I cannot explain it in detail unless you like to spend another 30 minutes on this. But believe me, this is beautiful. And this noise spectroscopy was a completely new approach, which allowed us also to produce, at the time, the longest decoherence time in the system. So this is just showing how our predicted frequency agrees with the experimental data. And this is the coupling of two qubits, again, based on calculating and observing certain term, which this is experiment, this is theory, and if we didn't have this coupling, this quantum coherence, the result would be looking like this instead of what it was. So it was nice. It was really good, and it allowed the company to build a solid foundation for developing technology further. Now, you know, it is a public company, and its valuation jumps back, well, up and down. You know, this is a volatile market, but it is closer to 10 billion. So not bad, not bad. Not many companies have this kind of valuation, actually. About 5,000 companies only in the States. So not bad. Now, what is so useful and interesting in this superconducting stuff? You can actually build a qubit, consider it as an artificial atom, and consider the system as what now is called circuit quantum electrodynamics. So, for example, you can have qubits like atoms in a cavity, and you can couple them using intermediate circuitry. What is even more interesting is that you can couple certain kinds of qubits to microscopic noise sources existing in the disordered part, say, of the tunneling barrier, so-called two-level systems. They may behave in a quantum coherent way, and then you can couple the state of your qubit to the state of this small microscopic structure, and so to speak, do quantum operation, transfer the state of the qubit to this thing and back. And because it is microscopic, it has better properties. It lives longer. And this experiment was actually conducted by the Martinez group and confirmed this prediction, so that you not only you have this quantum coherent oscillations of the state of your quantum bit, but you also can exchange its state with the state of this small microscopic structure inside. And if you do, as you can see here, the dark curve telling you the decay rate. It decays much slower than if you don't. The light curve corresponds to the evolution when you do not swap the state of your qubit with the state of this microscopic thing. Whether it can have any practical application, that's a different story. You cannot make them the way you like. You cannot control their properties, so this is more like a neat demonstration, a lab trick, rather than something for industrial applications. But still, it's nice. And this is very much like the cat whiskers diodes, which were used in early radio receivers, when you could find a sweet spot on the surface of some crystal, which would provide you with necessary nonlinear behavior, like in a regular diode. Well, this one-dimensional, or this circuit QED has lots of advantages, especially because you can control the size, the frequencies, the degree of decay, the connections, the whole structure of your device. And a direct experimental demonstration was of the fact that such quantum bit in one-dimensional cavity or strip line behaves indeed as a point-like atom in the microwave range, of course. So this is, by the way, a picture of such a qubit. It's just a loop, superconducting loop. What you see here, because this is micrograph, so you see the shades which were appearing here because of how you fabricate a Josephson junction here, here, and here. And it demonstrated all the properties of a point-like scatter. You see, experimental and theoretical predictions are very close. And also it demonstrated some resonant fluorescence, so behaving in a very nice way, confirming all our assumptions. So we have now quite a lot of technology under our belt. The question is what to do with it next. And what are the possibilities? Well, Here are different kinds of quantum bits, superconducting bits. As I said, there are more platforms than just that, and I describe several of them, but here I concentrate on superconductors. What you see here in the right lower corner used to be the biggest quantum computer in existence 20 years ago, because it contained 4 flux qubits connected. Well, of course, you need to put this whole thing in a big box, which covers the dilution fridge and everything else. But, well, this is the first commercial quantum processor. I have it in my room here. Well, 15 years ago, it contained 128 nominally quantum bits. Each of these sticks is actually an elongated loop, which is a fluxed qubit. And 4 qubits are overlapping 4 other qubits in the bottom row, in the back row, and these groups are also connected to each other. So this is an adiabatic processor, and it is very interesting because it is already pretty big, and this whole thing, centimeter by centimeter across, did behave in a quantum coherent way. So if we think about old Copenhagen approach, claiming in this interpretation that all quantum things must be microscopic and all classical things are macroscopic, this is the criterion which tells you which is which, even though you don't ever say where the boundary is. Now, at least for now, we see that there is no such well-defined boundary. As long as you can keep the coherence at bay, you can keep your quantum effects. And the last 25 years saw huge, unbelievable success in improving the properties of these quantum devices. If in 1999 the decoherence time for a superconducting qubit was less than 10 nanoseconds, now it exceeds half millisecond. This is only comparable to what happened to aviation. You have your Wright brothers' first contraption, which flew for fraction of a minute, and in 15 years you had German fighter planes, which for a while swept the allies of the European skies. But it is not enough. For standard quantum computing, gate-based quantum computing, you need more. You must have quantum error correction, you must have lots of extra qubits. The more qubits you have, the harder it is to maintain quantum coherence, so you need more quantum error correction and so on. So what we need still in order to make digital quantum computer is like going from here to here. Even in classical aviation, it took, what, 70, 80 years. So, and we don't want to wait for 80 years. We need to do something right now. And it is pretty pointless to get stuck on developing stuff for non-existent hardware or trying to build hardware when it looks like our technology is not there yet. We don't want this. But we need to do something. We should follow, for example, Napoleon's approach. We should try something and see what happens. Usually it works. In some cases, like in Russia in 1812, it doesn't. But what have we got to lose? So this is, by the way, one of earlier, so 10 years ago, structures of an actual quantum processor from D-Wave. Each point is a qubit, each line is a connector, and only the working qubits are shown here. And this is essentially an analog device, like a slide rule. The fact that we couldn't build Pentiums 150 years ago doesn't mean that we shouldn't use slide rules. These slide rules, in this case, it's a diabatic solver. So you try to build some structure which will have necessary properties so that the ground state of the structure will solve your problem. Fortunately, there is theoretical proof that you can do it always, even though it's not always realistic. But for many important things, like a problem of, a commercial traveler, you can do this. And moreover, for this kind of problems, you don't always need an exact solution. If you're looking for the most efficient path, if you get not the best solution, it will be still better than anything else. And it turns out that this kind of approach can give you good enough result, which is all we need. And as I said, this kind of devices is being used commercially already for all kinds of optimization problems, where it can give you either the faster result than classically, or better, or cheaper. Whatever works will be good enough. This is why there is so much stress now on so-called NISQ, noisy intermediate scale quantum devices, which do not require this huge overhead of extra qubits and extra operations in order to give something useful. They are adiabatic computers, quantum annealers, approximate quantum computers, and quantum reservoir computers. I will say a few words about that in a moment. This is something our group is dealing with right now. Well, the estimates for scaling for a quantum annealer are pretty nice, because logarithm of number is a very slow function. So we expect that this will not be too bad. And we have some useful ways of estimating how well things work, but speed up mathematically and scientifically is not that important, even though it is very important commercially. Now, speaking of quantum reservoirs, this is an interesting hybrid of quantum technologies and neural networks, or if you wish, artificial intelligence or machine learning. The idea is pretty simple. You have some quantum device, quantum system, which has rigid, not tunable properties, and you allow it to evolve. You input some parameters. For example, you send some signal here, or change some parameters of some bits of this system so that it encodes the input signal, and you let it evolve. It is nonlinear. It has very large, huge state space, and so different classes of behavior will fall into different outputs, which will be easy to analyze using simple linear regression software, and you get your output. This is a very promising approach. This is a development of classical reservoir computing, and it has advantages. Both the system can be much smaller and still have huge state space, and also it can take quantum inputs. Here we are. And we can also build kinds of antennas using quantum coherent arrays in order to get signals with sensitivity exceeding not just classical, but also so-called standard quantum limit, approaching so-called Heisenberg limit. And how much time do I have left? Excuse me, Pablo, how much time do you have?
Yes, we are finishing, Alex.
Okay. And then the problem is that we need to actually be able to build a qualitative theory of large quantum systems. So I don't have time to talk about it, unfortunately, but this is something that we must concentrate on. Building a qualitative theory of large quantum systems. And this is possible. There are theoretical reasons and some experimental data which tell us that this thing can be achieved with certain mathematical trickery. So hopefully next time I will be able to tell you what we've got. So far, we already obtained some initial results which allow us to believe that this kind of criteria, like Reynolds, equivalent to Reynolds number or other numbers in hydrodynamics, can be built for quantum devices. And thank you very much for your attention.
Great, Alex. Great talk. Thank you very much.
Not all, a pleasure.
It is amazing. Is there any question for Alex? Anything that you want to ask to him?
Maybe a very short question, Alexander.
Yeah.
Do you have plan to came to Latin America with this technology, or you came here?
Mm-hmm.
Do you have any plans to came to Argentina, to Latin America? I mean, making some opening offices or something like that.
I would love to. So far, unfortunately, I don't have any collaborations with South America. So, of course, this is a continent I never visited before. And I know that it has very good physicists, and so would be delighted if I had an opportunity.
Excellent. Thank you. We can create the bridges with Pablo and with all the community we have here.
You're more than welcome.
Thank you very much. And if you have a chance, please come to the UK, to Loughborough. We are the farthest point from the sea, so we have the best climate.
Excellent.
Yeah. Okay. So.
Thank you very much. I think, Pablo, you're in mute.
No, I'm not mute. No.
No, Pablo,
well, Alex, thank you very much for your time and for your kind presentation. It's amazing to see your path and what you have done. So thank you very much.
Not at all. Thank you very much for the invitation. Pleasure. Have a good day. Bye.
Bye-bye. Thank you.
Bye-bye. Thank you very much.
Thank you.